Yeah, so hi everyone. My name is Vaibhav. I'm a product manager in Google Cloud's networking product management team. Been working on infrastructure enhancements in cloud networking for secure optimized AI ML workloads. All right, so we'll jump a little bit into that further. All right, so just laying down the life cycle of AI/ML, you've got your training workloads, fine-tuning, and then finally serving an inference, right? And if you look at it from a network perspective, I just want to like map it out to what are the imperatives for each one of them, right? From your data ingestion side of the house, especially as there's a tremendous amount of data still sitting on premise, your fast, secure connectivity to your on-premises is critical, especially for training and fine-tuning jobs. Then when it comes to your training jobs, again, this is where I've made a number of enhancements in the GK networking stack, enhancing the scale as well as the performance. And that's, again, contributing towards accelerating your training jobs. And then we'll proceed to a bunch of innovations we've made on the inference side of the house, primarily also on GK. So on data ingestion, we have interconnect for your secure, fast connectivity to your on-premise environment, as well as cross-cloud interconnect for direct connectivity into third-party clouds. So wherever your data is residing, if you want to like train your models, fine-tune your models, leveraging that data, that sort of interconnect facilitates that high-speed data transfer movement. Next is on top, coming to your GK clusters. The GK cluster scale now is up to 65,000 nodes in a single GK cluster, effectively almost like, I think, 5 to 10 times what you have this in open source. And this is the same kind of infrastructure that is being used to train this is Gemini models or even some of the leading frontier models in supporting that sort of scale. And then finally, we'll talk a bunch of improvements that we've done in the cloud load balancing side of the house to deliver improved performance, especially for LLM workloads. So cross-cloud interconnect and interconnect, we're today at 100 gigs, but soon going up to 400 gigs. And also, we now are able to provide application awareness so that you can even apply some sort of priority to the type of workloads that need to get classified as high priority and ensure that you've got the fast data movement between on-premise and the cloud. On GKE, we now have a purpose-built RDMA VPC. So this is essentially using NVIDIA's reference architecture embedded within our Google Cloud network itself that enables you up to 3.2 terabits of non-blocking GPU to GPU connectivity. This is valuable not only for training jobs, and again, talking about scale of training, speak about the 65,000 nodes that we can support. So this is not just valuable from a training perspective, but even some of the large models, right? Some of the DeepSeek or even Llama 4, like some of these 600 billion parameter models are actually running across multiple nodes. And even when you're running an inference task, this sort of fast RDMA VPC connectivity improves performance. So now coming over to, so that was like kind of the some of the infrastructure benefits that we had across from just both training and inference. But in particular, when it comes to inference, there's a few unique challenges when customers are trying to run inference on scale, especially on Kubernetes infrastructure. Right? So the first one is that your accelerator GPU TPU capacity today is still constrained across various regions, right? And so customers are often scrambling to obtain GPU TPU capacity from different regions, different providers, wherever they can. Second one is how you distribute traffic across your nodes, across your pods is still an important consideration, and your traditional techniques are not exactly fine-tuned towards the workload profiles of your LLMs. And that's another area leading to uneven traffic distribution that, again, as a result, impacts performance. And then finally, how much of compute do you allocate for a certain model? It's a very dynamic problem, right? Essentially, it depends on the volume of requests that you're getting, the size of the model, the underlying GPU, the types of GPUs that you are, as well as what your latency objectives are for that workload. And so allocating that amount of compute is still kind of a uphill task for platform operators that we are looking to address. So we are looking at all of these problems and looking at from a GK gateway perspective, and we have enhanced GK gateway and the underlying load balancing capabilities therein, adapting them towards some of the unique LLM workload characteristics and addressing some of these problems. So with that, we have a GK inference gateway. This is your same GK gateway, but now optimized using certain extensions for optimized LLM serving. So what do we have? The first thing is we are load balancing rather than just doing it based off round robin or number of requests pending. We actually look at inference metrics coming from model servers, such as your VLMs or Triton or even Dynamo coming up, or even Google's own Jetstream. And we've done a whole bunch of benchmarking, and what we found out was that instead of just doing a round robin or looking at just the number of requests pending or number of sessions, what actually gives you the optimal performance is looking at your KV cache utilization of your model servers and your GPUs. Essentially, your inference process, the decode process, is often limited by how well you can reuse your KV cache. And if you're able to load balance using those metrics, it can actually give you improved performance. And we'll go a little bit deeper into that. Not only do we load balance, but we can actually even auto-scale based on these model server metrics. So going back to the problem of how much compute do you allocate, being able to auto-scale based on a certain threshold can actually dynamically allow you, based on the request load, as well as sort of your utilization of GPU infrastructure, and make much better use of your GPU infrastructure, efficiently scale without impacting performance. Secondly, we spoke about how your GPU TPUs are still constrained. And so typically what customers end up doing is that they deploy multiple instances of models on dedicated GPU TPU infrastructure. However, what they can also do is use a common base model, but use these LoRa fine-tuned adapters to actually multiplex and load multiple model use cases on a single base model on a single GPU TPU accelerator. So a practical use case of that, right? Imagine you have a global customer, you're serving models in multiple different languages for multiple different localities, right? Let's say I've got like German, Spanish, English. So typically if you've got fine-tuned models for each one of them, you would have to, let's say, deploy you would require, let's say, 3 GPU or TPUs. But now imagine that we've got a single base model, let's say it's a Llama 4, Gemma 3 model, but then I've got these fine-tuned adapters for each language model. I can actually better bend pack 3 of these models on a single GPU and thereby make more efficient use of my infrastructure. And our load balancing algorithms are now able to actually recognize the fine-tuned models and actually route to them with a certain level of priority as well. And this essentially helps you increase the density of your model serving deployment and make more efficient use of your accelerators. The other thing also is multi-region capacity chasing. So oftentimes, you might have a surge of load in your primary region, or your primary region might be out of accelerator capacity for whatever reason. In that case, rather than have multiple dedicated clusters per region and have to individually manage these regional stacks and the load distribution between them, that again is not a very effective use of your operations or of your capacity. You could have the single inference gateway that can route to regions wherever the capacity is available in case your primary region is out of capacity. So this is another way that you can have more efficient use of your capacity, and also use it across multiple pull it from multiple Google Cloud regions and use it as part of the single gateway. And then finally, we've seen that these LLMs, they themselves are sort of an attack surface, right? They themselves can be jailbroken. You can have prompt injection techniques, and also safety and security guardrails, right? So for example, how do you not serve harmful content? How do you have certain moderation policies? and also like just the observability around it. And so with that, we have integrated these sort of AI security tools, including Google's own Model Armor. We are partnering also with leading providers like Palo Alto Networks and NVIDIA's Nemo Guardrails to embed these AI safety security tools right at the gateway itself. So traditionally, your developers would have to embed these as part of their code. And that obviously is a fragmented approach, has its own challenges from a central security operations standpoint. But by integrating it right at the gateway, the platform and infrastructure teams now have centralized control over this and also provides a consistent level of baseline coverage across all models running in your cluster, in your environment. All right. So that was that. I just want to take a quick pause if there's a round of questions.
Yeah. Jim Sprinsky, CDC. So basically, you'd be able to intercept questionable internet traffic at this point by doing it this way, for example.
Yes.
Because I'm looking at the Model Armor. Sounds quite fascinating.
Yeah.
I'm not
So
sure if
it's,
you already mentioned that, or can you elucidate, or is it coming? A little bit more on that.
Yeah, so we are screening for requests as well as responses.
Okay.
And it is and we've got different categories of filters that you can apply at different levels of sensitivities.
Okay.
So there's filters around let's say racial content or hate speech and so on and so forth. And you can also define like the level of sensitivity against which you want to be able to apply each one of them.
Okay.
And you can also do it on a per model or a per use case basis. So let's say I've got a Gemma workload. Or I've got versus a Llama workload, I can have like on a per model basis, I can specify what model policies I want to apply.
That could be even interesting intra-language or between different languages, right? Something that could be offensive in one language,
yes,
or vice versa, right?
Yeah, that's right. Yeah, there's different aspects of language support as well.
Yeah.
You wouldn't have to look at how those are specifically supported on a per language basis, but yes, there's a language aspect to it too.
That would be impressive.
Isn't it sort of overkill to do like Armor versus some of the open source guardrail tools? I mean, I'd rather use those because they're emerging faster instead of using like a Palo Alto.
Yeah.
And then the second question is, does the gateway provide authentication and authorization? Because some of the other providers, the customers I'm working with, that's a key thing. They want to hook up like Okta to the gateway, and then that's the only way you get in within the organization. So is that sort of built into this as well?
Sure, yeah. So your first question, so our integrations are actually open in the sense that you can actually take one of your favorite open source tools. And it is a load balancer service extension. And so, just by writing a little bit of Go code, you can actually integrate as part of this service extension callout. And so, yeah, it's not limited to these providers. And we are looking at more contributions to this ecosystem. On your second question, sorry, I just lost that. Can you repeat that, please?
You're going to make me remember it now. No, yeah. Does the gateway include like integration to something like Okta for authentication and authorization?
Yeah, so one of the ways that, so there's two techniques that we've heard quite a lot of interest in. One is OAuth, and the second one is using API keys, especially from a user-facing perspective. Yes, we've heard requests for OAuth flows. And then, oftentimes, like a lot of the open providers, managed providers are using API keys to authenticate to models, and that's kind of request. So that's one of the integrations that we have on our roadmap coming, is to be able to support, whether it's OAuth, whether it's JOT token, whether it's API keys.
Clients want OAuth, and the other thing is that they're having to build their own with the other providers. In other words, they're having to create their own front-end gateway,
right,
and then do the hack to do that. So it'd just be nice if you already have the gateway.
Yes, exactly. So, our idea is that we just kind of federate the authentication to one of the existing IDPs providers and the existing mechanisms. Yeah. Yeah, so this is like something that we have like use case for deploying both for internal workloads as well as for like, if you want to if you're a model as a service provider and you want to avail of all of these benefits in optimized serving and more efficient use of your infrastructure, even you as an inference service provider can use this and expose your models out to the public internet. Yeah, so just going a little bit deeper into the optimized load balancing that we have, right? So essentially, think about your GPU TPU infrastructure as think about almost as cattle versus pets, right? In your traditional workloads, your web service requests, think about them as cattle. You could simply like spray them, best effort, round robin. But with respect to your inference requests for these GenAI workloads, every single GenAI workload request is like almost like 10^6, 6 orders of magnitude as computationally intensive as a traditional web serving or even traditional inference request. And how do you, as a result, land that every single request on the least loaded GPU has a very big impact on the efficiency as well as, not just for your own workload, but even as an aggregate, right? And so because also each of these LMs requests could have such a highly variable processing times in the order of like seconds to minutes versus traditional requests that complete in the order of milliseconds, if you simply go with round robin load balancing, you might end up on a GPU that is highly overly loaded, and that affects your serving latency, throughput, and the effective end user experience, right? Especially if you're using like a chatbot where the user experience really matters. And so by looking at, which is the least loaded GPU, not just in terms of the GPU utilization, but actually the KV cache utilization, right? Which is the most computationally intensive aspect in an LLM, inference decode process. Actually looking at that particular metric and looking at the least loaded model server to route to actually helps you get the best performance. In our own benchmarking, we found out we are able to achieve 60% lower latency and 40% higher throughput of inference serving using these optimized load balancing mechanisms.
So the optimization is based on model, like the GPU TPU utilization by model.
Yes.
Right.
Yes.
What about in situ like metrics? Because something like more than 50%, maybe 60-70% of models used in a lot of organizations are trials, or like there's a great, it could be the same model
exactly
used for different applications, and have much more variable usage patterns and also different priority levels. High latency may not matter for a lot of lab experiments. Lab experiments on the model, not necessarily scientific. That accounted for in this?
Yeah, absolutely. So what we're able to do is every single model deployment, you can have it assigned a unique model name according to the, and this is again, all based on the OpenAI API spec. And the gateway actually now has been enhanced to actually route looking at the model name in the body of the requests. And based on the name of the model, which again could be mapped into like, hey, this is a production model for a certain use case versus a development trial. Even for the same sort of base model, right? You've got like Llama for dev test versus Llama for like some production chatbot. You could name it differently. And the client request that comes in, we look at the body of the request. And based on that, we can prioritize it differently. And we can also like autoscale it independently.
That's good.
And so, there's a serving priority element. There's a model name aware routing that is also compliant with the OpenAI API spec. That's a key enhancement we've made. And then we've got the auto-scaling element. And of course, underlying whatever is the node pool, the characters of the node pool, you can assign that differently.
Okay, great.
Yeah. And this again goes back to your earlier point is like, you can set different auto-scaling thresholds for your production workloads with dev test and make sure that, you've got like, let's say your production workloads are always like auto-scaling at 80% utilization to ensure that they never get fully saturated versus you can maybe oversaturate your development workloads a bit more.
The only thing is this is roughly a tagging process. I mean, obviously prioritization, that's, a human quality, but there's not if someone forgets to name it dev test.
Sure.
So you're not capturing live telemetry, let's say, to figure out how it's being used. You're not shifting it that way. It's based on the
very much so on the deployment infrastructure and your
but still that
keywords there.
That's pretty important because the variability in usage has a lot to do with all the experimentation that's going on right now,
Exactly.
as opposed to production, large scale, which can happen on its own as well.
Exactly.
Okay.
Exactly. Yeah. So that's one use case. The second key use case we hear is that customers have got batch workloads, or like from a pub sub queue that is not so latency sensitive, like jobs that can wait on, like, let's say a certain queue and can return back to the user offline, versus real time online jobs like chatbots and stuff, right? And so you can assign a chatbot like a more latency sensitive critical priority, versus if it's like a reasoning job, an agent, or an offline job or a batch job, you can assign it like a standard or a sheddable priority. Yeah.
I'm Mitch Ashley with Future. And I'm curious, your nodes here, the inference gateway, is what you're running on Kubernetes, the gateway standalone across all of those nodes? Are you mixing any other application code in those nodes as well? Or is this strictly the infrastructure layer that other nodes get to call other?
It's really strictly the infrastructure. In fact, it's really nothing but, the gateway API is the instantiation. That's how customers instantiate it. But underneath the covers, it's a cloud load balancer. And it's the cloud load balancer routing to your pods and your GK cluster.
Okay.
You used the autoscaling reference earlier, but a prior slide, you also indicated the openness integrating.
Yeah.
And so you had like a Palo Alto logo I saw, really small, but it was there.
Yeah.
And so I'm wondering, is there an auto-scaling and licensing implication as that auto-scale occurs to maintain that secure AI by design, I think is what they would call it.
Right.
Is that auto-scaling handled by you?
Yes, the autoscaling is part of the GK infrastructure, the horizontal pod autoscaler, and the load balancer essentially then autoscales to all of the new pods that are spun up. And as far as the openness concerned, like that is an existing cloud load balancing feature. It's called service extension. It's a data plane extensibly pattern actually based off of Envoy. Our cloud load balancers actually are based off of open source Envoy.
Yep.
And is the same open source extensibility, service extension, data plane extensibility that we are using and integrated as part of Inference Gateway.
And so there would be no lift on the customer's part to have that Palo Alto instantiated and managed and maintained. That would be handled by Google?
No. So Palo Alto's the AI runtime security is still a SaaS service.
Still
and
SaaS.
so it's still, it's a SaaS consumption model. But essentially it's a gRPC call out to their SaaS service, the inspection and response. Yeah.
Yep.
Yes.
Looks like the inference gateway supports a lot of NVIDIA metrics from DCGM.
Yeah.
Does it also support metrics from your TPUs as well?
Yes. So the two key model servers that we are supporting, NVIDIA Triton and VLLM. VLLM is the most popular open source project probably in the inference space, and also like one of the most popular model servers out there. And so with VLLM, we recently introduced server TPU support. And so the same extensions, same optimizations are now also applicable to TPUs. And then we are also looking at, so Google also has their own Jetstream model server. And so we're also looking at supporting Jetstream, which will support TPUs. All right. Yeah, and I think you might have seen this slide earlier, but yeah, it's just kind of reiterating the point of, essentially load balancing based on KV cache utilization. And so on the left-hand side, you see like a lot of variability in the utilization across your model servers. Some of them are getting saturated. What that means as a result is requests start to get queued up, leading to higher latency, versus when we try to do load balancing based on KV cache utilization. Under the same load conditions, we actually see no queuing, and you see that your response times, your latency remains consistent, even in higher load conditions. Yeah, and this is again just highlighting how we are able to more densely pack multiple models on common set of GPU TPUs, and at the same time, how do you also fair share capacity across all of them by applying the serving priority we just touched upon earlier.